And then there's the bioengineered cornea project with Professor Gerard Sutton. This is really one of the most complex projects we've been involved in. It involves taking a donated cornea, and our colleagues from QUT have developed cellular processing methods to extract the 3 different types of cells we need from a donated cornea, and to process and build up those cells so that we can actually create 30 bioengineered cornea. Hi, I'm Gordon Wallace. I'm a Professor of Materials Science working here at the University of Wollongong, which is located just 80 kilometres south of Sydney. I've been incredibly fortunate to meet key collaborators along this exciting journey. It seemed like key collaborators that came along just at the right point in time. I've been fortunate to work with Nobel Prize winners, Alan McDermott, in terms of developing new materials. Incredibly fortunate to work alongside Professor Graham Clark, who really sparked my interest in the use of materials in medical technologies. Graham is the inventor of the cochlear ear implant, and more recently inspired by the clinical collaborators that I work with, including Dr. Payal Mukherjee in the 3D printed ear project, Professor Jonathan Clark in 3D printed bone, Professor Fiona Wood in skin regeneration, and also Professor Peter Chung in cartilage regeneration. There are numerous other clinical collaborators that I work with, but they're just examples of those clinical collaborators. And our biggest project at the moment is working with Professor Gerard Sutton on the Bianco project. Bianco, the bioengineered cornea. This is really taking a project from very fundamental discoveries through to a manufacturing line for bioengineered cornea. With Professor Fiona Wood, we're involved in a project that's aimed at skin regeneration. Fiona, of course, pioneered the spray-on skin technology for dealing with burns victims. We've been working with Fiona in adapting that technology, which really uses the cell recovery and the cell processing elements of that, but combines it with 3D biofabrication in order to print directly into the wound, directly into the burn, in order to facilitate skin regeneration. With Professor Peter Chung, an orthopedic surgeon at St Vincent's Hospital in Melbourne, we've been developing strategies around cartilage regeneration in the knee. That project has expanded to include the work we do with Dr. Payal Mukherjee in terms of cartilage regeneration to form a 3D printed living ear. And still in Sydney with Professor Jonathan Clark, we're looking at bone regeneration, particularly bone regeneration in the jaw after traumatic surgery, usually for cancer treatment, for example. There's a necessity to regenerate that bone. And then there's the bioengineered cornea project with Professor Gerard Sutton. This is really one of the most complex projects we've been involved in. It involves taking a donated cornea, and our colleagues from QUT have developed cellular processing methods to extract the 3 different types of cells we need from a donated cornea, and to process and build up those cells so that we can actually create 30 bioengineered cornea. So we take those cells and then we take collagen, which is extracted from human skin, using protocols that we've developed as part of the consortium. And then we develop new innovative fabrication technologies to basically build, using automated approaches to build a bioengineered cornea. It's a very complex structure. The middle part of the cornea, the stroma, is an exquisite arrangement of collagen in fibrils, and those fibrils form very thin layer membranes and we build those up in a fabrication process that we've developed here as part of the project. Our ultimate goal and the measure of success is a manufacturing line for bioengineered cornea. There's a real shortage of cornea around the world, and this approach will enable us to meet that shortage and to provide cornea for implantation to cure corneal blindness around the world. What's common in all of the areas of bioengineering in which we work is that we're addressing a clinical problem brought to us by a clinical team, and we do that by combining appropriate materials, biomaterials, with appropriate cells in a three-dimensional configuration which meets the challenge, which enables that tissue regeneration, whether it's bone or skin or cartilage, or be it the bioengineered cornea. It's all about identifying the right materials, the biomaterials, introducing the right cells in the right arrangement in the 3D structure using innovative means of fabrication. In terms of international collaborations, we've been fortunate to work with colleagues in Ireland, at Dublin City University and Trinity College Dublin, in developing new materials for medical applications. We also have collaborations in Canada at UBC, again, new materials for this time artificial muscle applications, but also for spinal cord regeneration in a project called Mend the Gap. We have collaborations in the USA at the University of Arizona, which is looking at neural engineering, so actually looking at using electroceuticals in order to fix medical conditions. There's various collaborations sprinkled around the world in Korea, Japan and China, all really looking at that fundamental materials discovery, but with an eye to applications either in medical or in the energy sector, and again, using those energy applications for medical solutions. Over the years, we've been fortunate to attract funding from the Australian Research Council in terms of our discovery work, from the National Health and Medical Research Council here in Australia as well, and more recently, the Medical Research Future Fund. And the Medical Research Future Fund is really all about taking the discovery right through to clinical impact. It's a fantastic means of support. That is the fund that is supporting the Bianco adventure and also supporting some of our work in the cartilage area. Some of the other funders include the Parson Williams Foundation, critical elements of funding, particularly supporting younger career researchers through fellowships, whether they be scientists or engineers, and often funding them to work together. So that's the collection of examples of funding that have been critical for our progress over the years. The passion comes from the desire to actually deliver real clinical solutions to those people that need them. Fundamental discovery in materials science is exciting in itself. When you see those fundamental discoveries translated into a real medical solution that is assisting real people, that's next level excitement. That's what gets everybody bouncing out of bed in the mornings to confront the challenges, because these are not simple tasks that we undertake. There's lots of disappointments along the journey, but for every success, every successful clinical deployment is such an exciting point in our journey, and it gives us all the passion to keep going, to keep confronting those challenges and keep delivering those solutions. I was fortunate to have a concerted period of time in my journey to Australia on a boat, which took 6 weeks, and during which my father forced me to learn how to play guitar. And I've been playing that guitar ever since, and enjoy now playing that guitar with both of our kids, one who also plays guitars and the other who's an Irish dancer. So I really do enjoy music. I also enjoy sport, in particular AFL. And I love Geelong and I love heading Collingwood. So there are a couple of passions that really get me going. And you can ask my daughter, I'm a fantastic Irish dancer as well.